I'd like to work through a problem with you from chapter 3 where the substance is an ideal gas to sort of illustrate uh, a very typical problem solving when you have a closed system undergoing a process that involves an ideal gas. So let's go ahead and get started. This was problem 379. And here's a little sketch. So let's look at the problem statement and then we'll start with a sketch and then plan our work. It says, as shown in the figure, 2 kilograms of oxygen fills the cylinder of a piston and cylinder assembly. There's the sketch. The initial volume and pressure are 2 cubic meters and 1 bar, respectively. It says heat transfer to the oxygen occurs at constant pressure until the volume doubles. Determine the heat transfer for the process in kilojoules, assuming the specific heat ratio is constant. It says K equals 1.35. Kinetic and potential energy effects are ignored. And the nice thing is you're provided with a sketch. So let's look at that sketch. Let's start with the sketch. And you'll see what I did in my solution is that I just took a screenshot of what was provided, but I did add a little bit to it. I'm trying to show very clearly that heat is being added, so I'm making that a little bolder. But also, do you see that I'm showing that there is work out? In other words, this piston is moving, volume is increasing, piston is moving, so it's doing work against the surrounding atmosphere. And so sort of an interesting thing about this problem, it's not exactly lifting a weight, but the piston is doing work by displacing some of the atmosphere. And so I have shown 2 dashed lines. Here's my initial closed system. And then the other dashed line is my final closed system. And on my sketch, I'm starting at state 1 and ending at state 2. So I've tried to enhance the sketch a little bit. Let's look for some key words and clues are just given in the problem statement. So when I see oxygen, I'm immediately thinking ideal gas. I see the word piston and cylinder along with the sketch. That tells me I've got a closed system. And there's my ideal gas. It says, and I'm going to say that we've got a quasi-equilibrium process saying that this piston is moving slowly as heat is added slowly. And let's see, it does say constant pressure process. So that's going to be key for us. That's a good clue. And also, and what we're asked to find is heat transfer. And one thing that I learned after taking, not exactly the first time in thermodynamics, but in a second and third course in thermo, when I learned that whenever I see what is the heat transfer, that tells me I'm going to be using the first law of thermodynamics almost assuredly. When I see I need heat transfer, I'm going to need to write down the first law. Now, and we're going to go through that, and you're going to discover here, and you see in the given information, you don't have T1 and you don't have T2, so you don't have any temperature. So that's one thing to observe that you don't have, but you're going to be able to find that you have enough information for the ideal gas to figure out T1 and T2. Even though you're not asked to find it, of course, you're going to realize that you're going to need the 2 temperatures, T1 and T2. Oh, when you read this problem and look at the sketch provided carefully, you'll see that there's a subtle point to make. There's a discrepancy. Notice here in the words, it says the initial pressure is 1 bar. And in the sketch, it says the initial pressure is 1 atmosphere. Now, sharp students are going to know, they're going to point out, that's inconsistent. 1 atmosphere does not equal 1 bar, does it? So that is a subtle inconsistency. But as an engineer, as a young engineer working towards becoming a practicing engineer, this is a good opportunity to say, look, I've got to use some common sense and I've got to make a decision and figure out how to keep marching ahead instead of just pointing out this inconsistency and quitting there, just waiting for future instructions. 1 bar doesn't exactly equal 1 atmosphere, does it? However, 1 bar is about equal to 1 atmosphere. I think 1 atmosphere is about 101 kPa, and 1 bar is 100 kPa. And so look, let's just continue with a numerical solution saying that P1 equals P2 equals 1 bar, or we're going to need units of kPa. So let's just stick with P1 equals P2 equals 100 kPa. We've made a decision. We're going to keep marching ahead. Let's do a little self-mental quiz before marching ahead about what I think you should know now about any ideal gas. Any ideal gas, there's some things that you know. So my suggestion is all these things in the green text box should be in your head now. You shouldn't depend on a formula sheet or going back to the textbook to know these things. R is R bar over the molecular weight. What's R bar? That's the universal gas constant. And look at this. I have incorrectly, I've got my units written improperly another time. R is 8.314 kilojoules per kilomole degree K. So I've overlooked that. Kilojoule per kilomole degree K. Ideal gas equation of state, PV equals MRT. You should know that. And remember, that's for any ideal gas, not for steam, not for phase change substances, for any ideal gas. And then you also know P times little v is equal to RT, that you just remember the definition of specific volume. Another thing you know is delta U, change in little internal energy, is the integral of CV dt. That's for any ideal gas. Delta H, the change in enthalpy, is the integral of Cp dt. Okay, so that's an integral. For this problem, we're going to show that Cv is a constant number, so it's going to make life a lot easier to solve this problem. But anyway, I do want to suggest that these things you should have in your heads for an ideal gas. And let's see, if you do not, I'd suggest you go to my Jay's Toolbox Videos YouTube playlist called Thermodynamics Ideal Gas, and suggest that you watch 3 videos, Ideal Gas 01, Ideal Gas 02, and finally Ideal Gas 03. And 03 has a lot of details about dealing with specific heats and dealing with changes in enthalpy and internal energy. And so I want to suggest that this is a part of the hard work that you've got to invest in class. To gain success in this class, you've got to do some hard work. And part of that is really, really learning and committing into your mind the fundamentals associated with ideal gas substances. Okay, so another thing, we're looking ahead, and I do want to suggest that CP and CV are disclosed in this problem, and they're disclosed by way of stating K equals 1.35. And so I hope that you remember K, the definition of K is CP over CV, and it's given as 1.35. Okay. And so what I can drag you through here to show you that, well, K is 1.35, and that's CP over CV. Recognize that for any ideal gas, CP minus CV is equal to R. So I can substitute for CP, this term, R plus CV. So I can solve to get a numerical value for C sub V as long as I've got R. And that's easy for oxygen, isn't it? Okay, and so when you find in the problem, if you need to find delta little u or delta little h for this problem with constant specific heat, delta U is simply CV times delta T, and delta H is simply CP, some constant number, times delta T. We've done some pre-work before we really get into crunching numbers here. Okay, so let's plan our work. How are you going to solve this problem? So here's our sketch. I've replaced 1 atmosphere with 1 bar in our sketch, okay? And you've got the sketch, feel pretty good about drawing it. And then as a newcomer, you might say, well, okay, I've got the sketch, but I still don't exactly know where to start. And one of my favorite professors drilled into our heads, if you've got your sketch, but you still just don't know where to start, Try writing down the first law. Just try writing down the first law and see if that helps you. And this is a case where definitely that's going to work for you. So we'll write down the first law for a closed system, Q in, that's what we're looking for, minus W out equals delta capital U. That's going to be M times delta little u, or M times U2 minus U1. Is there anything in our experience so far that we think we can get as we drive towards getting a number for Qn? I think the answer is, of course, yes. The work out for this closed system quasi-equilibrium process is the integral of PDV. Your sketch, your common sense now says, wait a minute, for this problem, I've got constant pressure, P1 equals P2, so I can simplify the integral to say that the work out, I can get a number because I've got the pressure and I've got the two volumes, V1 and V2. I can get a number for W out. Okay, what can I, mass was given, check. What can I do for U2 minus U1? Can I get that? Well, not straight out, but I do know that delta U is the integral of CV dt. CV is constant. Look, wow, all I need to do here is get a value for CV. I hope I've showed you that we can get that with given information. So delta U, U2 minus U1, is simply going to be the number CV times T2 minus T1. Oh, but I need T1 and T2. How am I going to get that? I'll use the ideal gas equation of state. So that T2, P2V2 equals MRT2. And so you see that I've written down T2 as P2V2 over MR. And also then solving flat out for T1 in the ideal gas equation is P1V1 over MR. So we're going to use ideal gas equation of state to get T1 and T2. And so this is sort of an overview of how to solve thermo problems, because what you're doing is kind of, when you plan your work, you're kind of backing up. What you can do is back up. And so you say, well, I've got to get C sub V. I've got to get C sub V. And then I can also, and I got to get R. If I can get R, I can find T1 and T2. And then I'm going to back up. I've got T1 and T2. I've got to get a value for CV. I can get that. So I can get U2 minus U1. So I can back up. And now I'm all the way back to my first law. I'm satisfied I can get a numerical value for the work. Mass is given. And now I can get a numerical value for U2 minus U1. So do you see that this problem solving is sort of a backing up process if you think through what you're going to do first? Okay, let's work on the work first, because that's the easiest. I've drawn a PV diagram so I can visualize what is the work out for this process. Well, it's the area of this rectangle, P times delta V. So let's just do the integral. V1 is 2, given. V2 is double V1, given. It's 4. P1 in bars is 1. But I've got enough experience now to know I've got to get my pressure in kPa to get my units straight, to get work in kilojoules. Kilonewtons per square meter times cubic meters will give me kilonewtons, which is a kilojoule. So I do the math, I keep my unit straight, and I've got the work done from 1 to 2 is 200 kilojoules. Now that's not what was asked, but we're getting well on our way to solving the problem. Work out 200 kilojoules. What's the next thing we do? Let's get the gas constant and a value for C sub V. The gas constant is R bar over the molecular weight. Should know molecular weight of oxygen off the top of your head from college chemistry. It's 32 kilograms per kilomole. And here I see that I've written my units for R bar out correctly. Shame on me for not doing it in that green text box. So R, 0.2598 kilojoules per kilogram degree K. Given K is 1.35. I'm going to do the algebra to solve for CV. CV is R divided by K minus 1. So that's not a formula, is it? CV is R divided by K minus 1. You'd be foolish to put that down as a formula on a formula sheet if you're allowed to have one. You can derive that in a matter of seconds to get that CV is 0.7423 kilojoules per kilogram degree K. So we're moving along. What's our next step? Determine T1 and T2 using the ideal gas equation of state. I've got R, I've got M is given, P1 in kPa, V1 is in cubic meters is 2. So ideal gas equation of state gives me T1 is 385 degrees K. Same drill for state 2 to give me T2 is 770 degrees K. So I've got both my temperatures now. Okay, so let's see. We're going to apply the first law. I think we've got everything we need to get our final homework result. Mass was given. CV, we found it. T1 and T2, we found it. The work out, we kind of did that first. We've got it. So now it's a matter of plug and chug to get Q in is 771.43 kilojoules. And that's it. That's the homework problem. Now, you may have talked about this problem in class or something similar. And you may have observed, hey, my instructor solved this problem differently. Wow, what's wrong here? What's going on here? How is it possible that we've got two different solutions? So I do want to point out, and I'm going to show you maybe how to do it differently, how to solve this problem differently, and point out that in many engineering situations, different numerical approaches are possible, but we're using the same fundamentals and we're going to get the same numerical result. Different approaches are possible, but same fundamentals. So here is an alternative method for finding Qn directly without needing to find the work. Now, I have to refresh my memory, though, on what is the work. I'm not going to numerically calculate it, but work is the integral PDV. And so refresh your memory that the work out in kilojoules is M times the pressure for our constant pressure process times delta little v. All right. Well, let's jam that into the first law. Here's our statement of the first law. We'll rearrange the first law. Qn is M delta U plus W out. It's just rearranging. We realize that delta U is M times U2 minus U1. Got it? Okay. Work out M P times V2 minus V1. Now let's get a little clever here on this. Let's collect our mass terms. Here's our U2 minus U1. And let's recognize that P times V2 is P2V2. And let's recognize that P times V1 is P1V1. That's for this constant pressure process. We've got kind of a special process going on here. Now we're going to visually look. Let's look at this term, U2 plus P2V2. That's the definition of enthalpy, H. And let's look at this term, minus U1 minus P1V1. That's also the definition of enthalpy, H1. So we can collect terms to get Qn is M times H2 minus H1. And for an ideal gas with constant specific heat, H2 minus H1 is simply Cp times T2 minus T1. So look at that. So we've got a little bit of a very specialized formula for this one homework problem. So let's go ahead and do the numerics. Okay. So here we go. We've got, we had R and CV from previous work. So we'll calculate Cp 1.0021 kilojoules per kilogram degree K using Cp minus Cv is R. We've already found T1 and T2. We're given M, and so we're going to do the numerics. Qn is M times Cp times T2 minus T1. It equals 771.43, and lo and behold, it is the same numerical result as calculating the work first. And so kind of an important point that I'd like to make to you is that there is a pitfall of blindly writing down a specialized formula for a specialized homework problem and believing that's going to help you on a quiz or test. There's more pitfalls to that on a formula sheet than there are benefits. And You're going to be able to discuss these subtleties a little bit more if you choose to go to graduate school. I'm not going to discuss those now, but I did want to point out to you that there are two methods for solving this problem. They are identical because both of those two methods use the same starting fundamentals. Okay, I hope that's helped. I hope it's helped you solve this homework problem if you've chosen to work on it or been assigned it. And the other part is recognizing that in some cases, there's different ways to solve problems, but you do have to recognize that we all start with the same fundamentals. Here's our recap. Start with a sketch. Always start with a sketch. Plan your work before crunching numbers. Plan what you're going to do so you don't waste time maybe crunching numbers on things you don't need to crunch numbers on. Start with the fundamentals, writing them out, kind of like we did. Okay. Blindly using specialized formulas is a loser. So I really want to make that point is either shopping around for formulas that might work in the textbook, that's a loser. And certainly trying to copy down lots of specialized little formulas that apply to little specialized things on a formula sheet, that's a loser as well. Focus on the fundamentals and getting things into your head and not depending on written down formulas. Check units as you go along. So there was a couple of situations in this problem we had to remember about working in kPa, not bar of pressure, and express your results including units. And in my work, I try to work all the way down through the solution with units throughout my solution, not just including units in the final result. Okay, that's it. So I would classify that problem as maybe easy to moderate. If you've never done it, if you're not familiar with doing piston and cylinder problems, would be moderately difficult. If you've done a lot of piston and cylinder problems up to now, would be pretty easy. Maybe except for the details. I've got an ideal gas. What do I do? I need properties. How do I get CP? How do I get CV? Can I treat CV as a constant value? Those are things that will come to you more naturally the more and more problems you solve. So I hope that's helped. And also recognize in chapter 3, we're dealing mostly with closed system problems, but we have two categories of problems: substances that can be treated as ideal gas, like this one, and other substances that would be phase change substances like steam, refrigerant R134A, ammonia, and substances like that. So hope that helps. And please join me as we work through problems in the next chapter as well.